The next part is to determine intervals of concavity. To determine intervals of concavity, we need to find the second derivative. So how do we find the second derivative? Well, let's go back to the actual first derivative, not the factored one where we divided by -3. Let's look at the original first derivative, which was -3x squared plus 6x plus 9. And now from that, we can find the second derivative. The second derivative would then be, using the simple power rules, sum and difference rules, constant multiple rules, you'd have -6x plus 6 is your second derivative. Again, we need to find when is the second derivative equal to 0 or undefined for possible inflection points. This is never undefined as it's a linear function or a polynomial function. So let's go ahead and set this equal to 0. Subtract 6 from both sides. You'd have -6x equals -6. Divide both sides by -6. And I'm ending up with x equals a positive 1. Just like we did on our previous problem with the first derivative, we're going to create a number line and break it up at that point. Now, though, we're not looking at what's the sign of the first derivative, we're looking at what's the sign of the second derivative. At when it was 0, we look at what intervals we have to consider. It would be -infinity to 1 and 1 to infinity. We go ahead and we create a testing chart, the sign chart, where we plug it into the second derivative of the function. Again, the second derivative was -6x plus 6. I need a number from the first interval, how about 0? And a number from the second interval, how about 10? I plug those numbers in, use a calculator if you must. If I plug in 0, quickly shows me that the second derivative is positive. So in that entire interval, the second derivative must be positive. I plug in a 10 and I'm going to get a negative. So the entire interval, that second derivative must be negative. Again, anytime that my second derivative is positive, I know that my function is concave up. Anytime that my function is negative, my second derivative is negative, I know that my original function is concave down. And any point where it changes concavity, which would be at x equals 1, I know that has to be an inflection point. Again, this needs to be an inflection point is a point on the graph. So I need to find out what is the actual value of f of 1, the point on the graph, to find the inflection point. So let's go back in and plug that into our original function. So if you remember our function, it was -3, and then it was our original function was -x cubed. So that would be negative, and then we'd have 1 cubed. And then it was plus 3x squared, so that'd be plus 3 times 1 squared. Then it was plus 9x, so that'd be plus 9 times 1. And then it was minus 27. So there we have our minus 27. So when we find our f of 1, go ahead and plug that into your calculator if you need. I'm getting a value of -16. So what does that tell me? That tells me that the point 1, -16, is an inflection point, a point where it changes concavity. So let's put it all together. Again, concave up is where the second derivative is positive, which was the interval -infinity to 1. Concave down is where the second derivative was negative, which was the interval 1 to infinity. And then we had an inflection point at the point 1, -16. That gives me another point to use on my graph. If we look at the point 1, -16, that's an actual real point that I could plot. And then I also have information about the concavity, which we will use in the next section. Okay, so let's go on to the last part. Now that we have all of that, what I argue is we can sketch a rough graph, and a very accurate rough graph. When I say rough graph, the only thing that's not going to be accurate will be the y values of this graph, okay? But we can sketch a very accurate shape-wise diagram of this entire graph. So how are we going to do it? The first thing that I would do is suggest going back through parts A, B, C, and D, and finding any important parts, any points where we broke it up, and any points that we know are on the graph. So, for example, in part A from the previous problem, I noticed that I had x-intercepts at -3, 0, and 3, 0. So I'm going to do some little tick marks here. how about -1, -2, -3? I'm going to plot a point here and call it -3, 0. And then the point, try to keep the scale the same, 1, 2, 3. I know I have another point at 3, 0. Okay. I also knew that I had a y-intercept at 0, -27. 0, -27, well, that's pretty far down. So our y-scale is not going to be too accurate right here. So I'm just going to make up a point right here, and I'm going to call this the point 0, -27, right about there. I don't even need to put tick marks for scale for the y value. That's not important. Okay. Let's move on to part B. What did I have? Well, the places that I broke up in part B, where I broke up the intervals, was at -1 and 3. So what I'm going to do is just go ahead and draw a little dotted line here at -1. And I'm going to draw a dotted, and I'm going to extend it beyond the graph. And I'm going to also draw that dotted line at 3. And then what I want to do is I want to consider what happened to my derivative on those intervals. So I know it was negative at first, and then it was positive in the middle, and then it was negative at the end. Okay? I also know at that point, -1, -3, I had at that point, -1, -32, I had a minimum. And at the point 3, 0, I had a maximum. Well, if you look, the point 3, 0 is already plotted. And now I need to plot a point that would be -1, -32. So I'm at x equals -1. It looks like I have to go a little bit further down. So I'll do something like this right here. This will be the point -1, -32. So now I have taken all the information, except for the fact of increasing and decreasing, but I'll get to that in a second, from step B, analyzing the first derivative. Now I'm going to move on to step C from analyzing the second derivative. Let's look at what information we gleaned from the second derivative. Well, from the second derivative, if I look, where did I break it up on the chart? I broke it up when x equaled 1. So I'm going to put a dotted line at x equals 1. I know that everywhere before x equals 1, my second derivative was positive. And I know that everywhere after x equals 1, my second derivative was negative. So essentially what I've done is I've taken the two number lines that I created from B and C, and I've put them right there. I also know that there has to be an inflection point when x equals 1, and that's at that point 1, -16, so I'm going to try to rough it on the scale. I'll put a point right here, and I'll call this point right here 1, -16. Okay, so now I have all the informations from step A, B, and C on my chart. Okay. I need to go a little bit further and consider what is the shape of my graph on each one of those given intervals. So let's consider the interval from -infinity to -1. I know that my second derivative is positive, so that means I have to be concave up or a smiley face shape. My first derivative is negative, so that means I need to be decreasing, so it seems to me that I have to be, in that interval, the left half of a smiley face. In that interval, I have to be the shape of the left half of a smiley face. So what am I going to do? I'm going to go through the points in that area, and I'm going to make it the shape of a left half of a smiley face. Okay, let's continue on. Let's look at the next interval that it was broken up from, which was -1 to 1. From -1 to 1, I know my second derivative is positive. Again, that means it's a smiley face. But now my first derivative is positive, so that means I need to be the right half of a smiley face. So on that entire interval, I have to be the shape of the right half of a smiley face. So what am I going to do? Connect the points that I've already plotted, making it the shape of the right half of a smiley face. Let's look at the next interval. It seems the next interval would be from 1 to 3. My second derivative is negative, meaning I would be concave down or a frown. My first derivative is positive, so I have to be increasing. The left half of a frown is increasing. So this interval has to be the shape of the left half of a frown. So what do? I try to make my graph, connecting the points, the left half of that frown. Let's go to the last interval from 3 on. My second derivative is negative. Second derivative negative tells me I'm concave down. My first derivative is negative, which tells me I need to be decreasing. So which side of a concave down of a frown is decreasing is the right half of a frown. So it seems to me the shape of the graph has to be a right half of a frown. So what do? I go to the point, keep it connected, and I make it the right half of a frown. Using all the information that I got from A, B, C, I was able to put it together underneath the graph in D and sketch a rough graph. Notice now, especially if I was using something like WebAssign to do this problem, it says which of the following graphs is the graph of the function. I was able to get that graph without using a calculator whatsoever. What I encourage you to do now at this point in time is check your graph using a free software like Desmos, or if you have a graphing calculator, you could use the graphing calculator to check your graph now. Again, realize that our scale for y is ridiculous. It's not accurate at all. Very, very crammed compared to the x, but this would be the shape of the graph if you zoomed in and changed the window. So using these 4 steps, we were able to complete the graph and pretty much tell you everything you need to know about the graph of the original polynomial function. Again, we started by analyzing the function, determining domain, x-intercepts, y-intercepts. We looked at the derivative, which gave us increasing, decreasing, and relative extrema. We looked at the second derivative, which gave us concave up, concave down, inflection points. Put all that information together on one single number line, and that gave us a rough sketch of the exact shape of the graph on the given interval.